Hi everyone, my name is Hui Siyuan, an Intel software engineer. My main research interests include security, AI, and operation systems. Yuqiu, Albert, and Edmond are all my colleagues. We are from the same team. Our main work includes providing security solutions for cloud service providers in China. I will introduce the work of our team, horizontal federated learning and secure distributed training for recommendation system with Intel SGX. I will introduce the following aspects: background and problem, privacy protection with Intel SGX, horizontal federated learning, secure distributed training, experiment and conclusion. Recommendation systems have many applications in our society. However, the mode construction of recommendation system is often inseparable from users' data, especially for deep learning-based recommendation systems. Due to the complexity of the model and the characteristics of deep learning itself, its training process not only requires long training time and abundant computational resources, but also needs to use a large amount of user data, which poses a considerable challenge in terms of data security and privacy protection. Large-scale recommendation systems usually rely on cloud computing. We mainly consider two scenarios. In the first scenarios, data providers often have only a portion of the data within the company to build a well-performed recommendation system model. One solution is to train the model among different data providers collaboratives with their one portion of data. However, this raises the issue of data security. In the second scenario, some data providers don't have more abundant computing resources. When training recommendation systems, they may need to hand over the training tasks to cloud service providers with abundant computing resources. Issues like privacy leakage may arise in the process. To solve the problem in scenario 1, we propose a horizontal federated learning scheme. And to solve the problem in scenario 2, we propose a secure distributed training solution. The security technology in our solution relies on Intel SGX. Intel SGX can ensure the security of our scheme in the following three aspects. Firstly, Intel SGX guarantees runtime security. The gradient information is stored inside the Intel SGX enclave in the training phase of federated learning. Intel SGX provides assurance that no unauthorized access or memory snooping of the enclave occurs to prevent leakage of gradient and model information. Secondly, Intel SGX guarantees in-transit security. We use the remote attestation with transport layer security we called ITLS of Intel SGX technology to ensure security during transmission. This technology combines TLS and remote attestation technology. ITLS uses TEE as the hardware root of trust. The certificate and the private key are generated in the enclave and are not stored on the disk. Therefore, participants can't obtain the certificate and the private key in plain text, preventing the man-in-the-middle attacks. In this federated learning solution, ITLS is used to ensure the encrypted transmission of gradient information. Finally, Intel SGX ensures application integrity and confidentiality. To solve the problem of how to verify the untrusted application integrity, we implemented ITLS enhanced gRPC in TensorFlow to verify the Intel SGX enclave. It ensures that the runtime application is in a trusted version. We proposed a horizontal federated learning solution based on Intel SGX technology for the DRM. We adopt the parameter server architecture provided by TensorFlow. There are two types of training nodes, parameter server and worker. The parameter server nodes mainly saves and aggregates the parameter information of the model, and the worker node is mainly responsible for the performing forward propagation and back propagation during the training process. In the training process, each worker uses local data in its enclave to compute a round of training and then sends the gradient information in the backpropagation process in the parameter server through the ITLS technology. The parameter server completes the gradient aggregation and updates network parameters. Finally, it sends the updated parameters back to each worker. The training phase can be divided into 6 steps. We first use Intel SGX to put the participants run in different enclaves. Then works calculate gradient information based on local data in the enclave environment and send the gradient to parameter server through ITLS. Parameter server performs gradient aggregation and updates global model parameters in the enclave. Then the PIS sends the model parameters to works. The work uses this to update the model parameters. Steps 2 to 6 will be repeated continuously during the training process, since the works and the parameter server run in a memory encrypted enclave environment, and the ITLS technology guarantees encryption during transmission. This solution can ensure privacy during training. We implemented another secure distributed training scheme, which divides the distributed nodes into 3 classes: parameter server, work, and chief. The chief nodes have the information of the dataset and model. In terms of privacy protection, we also use ITLS enhanced gRPC to ensure communication security and remote authentication during the training process. All 3 distributed nodes above run in the enclave environment to ensure runtime security. The difference between this scheme and the horizontal federated learning is that the data is not stored in the worker node, but the chief node divides the dataset during training initialization and transmits it to each node through the network. This process is also under the ITLS enhanced gRPC framework to ensure secure transmission. In the experiment, we implement horizontal federated learning and secure distributed training on TensorFlow and test it with the DRM model. For both tests, we evaluate the training process with click-through record in Cargo Creator AD dataset, which contains 13 numerical features and 26 categorical features. We use Grameen, an open-source project for Intel SGX, can run applications with no modification in Intel SGX. For AI framework, we use TensorFlow, an open-source platform for machine learning. To justify the correctness and efficiency of our implementation, we collect and compute the loss, training speed, and accuracy, and compare with non-SGX distributed training. In the federated learning scheme, we set up one parameter server and 4 works. They each run in a Docker container environment. We tested and compared the performance of our scheme and the non-secure scheme during the same environment. The left graph is the training loss curve, and the right graph is the training accuracy curve. It can be seen that adopting our security scheme will not affect the training effect. Additionally, we tested the training speed of both. Adopting our scheme incurs about 2.2 times the performance over height. We also compared secure distributed training with no encryption. The left graph is the training loss curve. It can be seen that the convergence of the two trains to be the same. The right graph is the training time comparison. Adopting our scheme brings about a 1.6 performance penalty. In conclusion, we have done three things. First, we use Intel SGX to secure several key aspects of distributed training. Second, we propose the horizontal federated learning and secure distributed training schemes based on Intel SGX. Finally, we experiment with two training schemes on DRM models demonstrate that both schemes will not affect the training effect. It's important that our training time is also tolerable. Our horizontal federated learning scheme has been open sourced in CCZone community. CCZone is a collection of code-ready reference solutions which can be used as a copy-paste developer guide, demonstrating how to apply modern security technologies to real-life cloud business scenarios. It includes solutions based on encryption technologies such as TE, MPC, and HE. This project is run by me and a colleague of mine. Welcome to visit or join CCZone. Thanks for your listening.